with the oxidation number. We'll focus on the oxidation number for main group elements first. Well, for this class, the transition metals are a little bit more complicated because they have so many possible oxidation numbers available. And for this class, we'll just skip the transition metals for the oxidation number and just focus on main group elements. So the first thing first, what is oxidation number? The definition of oxidation number is effectively a convenient fictitious charge that we assign to each atom. So one thing to keep in mind, the oxidation number we write like +6, +2, -2. These are not real charges. These are just like charges, just like fiction charges we added there to help people annotate the atoms in a molecule. We have some general rules to assign the oxidation number, so we'll go over these general rules and then we'll do some practice together. First thing first, the oxidation number of all atoms must add up. So this is the essential rule. So the priority of these rules to assign oxidation number goes from most important to least important. So the first one must be fulfilled, and then the second one is, in order to fulfill one, it's preferably to have the second one and third one fulfilled as well. So it's like the importance reads from 1 all the way to the end. So first thing, when we say oxidation number of all atoms must add up. So if we take a look at the example here, we have lithium, say that's our group 1. Let me just pull out the periodic table on the side for your reference. So say lithium, that's one of our alkali metals, likely to have +1. And this entire molecule is neutral. What that means is the entire oxidation number must add up to be 0. So from there, we can derive that hydrogen must have -1, so that the entire molecule's oxidation number adds up to 0. Alternatively, you could also have a charged entire molecule. Well, this is not really a molecule, it's more or less a hydroxy anion. So in this case, the entire anion has a -1 charge. And here we have oxygen, so that's -2. And then hydrogen is +1. And adds up to be -1. So the number must add up. If you have a neutral molecule, it adds up to 0. You have an anion with -1, adds up to -1. And then these are just related, right? So here when we're talking about the alkali metals, normally have +1. If you think about it, as the alkali metal, their valency has just 1 s electron that's easy to be loose to reach that noble gas configuration. So in this case, on our second priority, you have group 1 elements, which are our alkali metals. They're normally +1 oxidation number. And then group 2 elements like our alkaline earth metal, they're normally +2 oxidation number. So that's on the group 1 end. And moving on to the halogen end, these are atoms that are electron negative. They want to gain an electron to reach the noble gas configuration. So our halogens are mostly -1 oxidation number. So, for example, if we have potassium chloride, this one is pretty easy, we can do. Potassium, that's our alkali metal, so that's +1. Chloride, that's our halogen, that's gonna be -1. And at the very end, we check it and everything adds up to be 0 and we're happy. There are exceptions for the halogen's oxidation number. So for example here, in this hypothetical molecule of ClF, we know that fluorine is fluoride is our most electron negative atom. This one is always going to be -1. It is more electron negative. then chloride. So fluoride is going to be -1. And we know the entire molecule must add up to be 0. So that deducts our chloride to be +1. And the entire molecule adds up to 0 and we're happy. So again, it's when you're assigning the oxidation number on the fluoride, that's the most electron negative one. So it's going to be a -1. And in order for the entire molecule to be entire molecule's oxidation number adds up to be 0, chloride must be a +1, and that makes an exception. All right. And then the next rule is for hydrogen. In normal cases, hydrogen will have a +1 oxidation number. And you can easily imagine there are exceptions, because now we're moving on down to our priority list. For example, if we have lithium hydride, I think we saw that before, right? So the lithium as an alkali metal always have +1. So if that is our +1, then hydrogen will be our -1, and everything adds up to be 0. So hydrogens are normally +1, but exceptions might be in metal hydrides. All right. And moving down our list to oxygen. Oxygen is pretty electronegative if you remember our electronegativity periodic trend. So fluoride is the most electronegative, and source go diagonal towards fluoride. So oxygen as fluoride's neighbor, it is pretty electronegative, which means it is most likely to be -2. So where that -2 comes from is oxygen can take 2 electrons to reach the noble gas configuration of neon. So that's where that -2 comes from. So for example, like if we're talking about water, which is a very common molecule, if you may. So oxygen is -2, hydrogen is +1, but 2 times +1, and adds up to be 0, and we're happy. So that's a normal case. There are some exceptions when you're assigning the oxidation number for oxygen. For example, when the oxygen binds to a more electronegative atom. So in this case, we know that fluoride is more electronegative than oxygen. Then if we have a molecule of OF2, then in this case, fluoride is always going to be -1. And there are 2 of them. So our oxygen must be +2. The second exception is whenever you have a peroxide bond. So in peroxide, or when we say peroxide, it means we have oxygen-oxygen bonds. So in this case, instead of oxygen being -2, you're just -1. Use the same color. And everything again needs to add up to be 0. So do that sanity check at every end, at the end of every practice. All right, so far when we were talking about assigning the oxidation state, we went over several rules. The most important rule is that these oxidation number must add up to give you the total charge of the molecule or the anion or the cation. And then we have a list of priority. So the first and the more important one is when you have alkali metals or alkali earth metals, they always be +1 for alkali metals, +2 for alkali earth metals. So And then for the halogens, the more electronegative it is, and the more likely it is gaining an electron. So the most electronegative atom, which is fluoride, always 1 electron, means it's always going to be our -1. Other halogens will typically have -1 oxidation number unless it is binding to a more electronegative atom. Then we have hydrogen, that's typically +1, but in metal hydrides, that's an exception. It can also, so because the priority is lower than an alkali priority. So hydrogen is normally +1, can be -1 when it's in metal hydrides. And then oxygen, when it's binding to more electronegative atom, that's going to be exceptions. Otherwise, it's going to be -2. All right. So these are the rules we went over. Now we're going to move on and do some practice together. Let's say the first one, the sulfite. So what we have is the entire ani has a -2 charge. So every oxidation number needs to add up to be -2. And in here, we don't know the oxidation number of sulfur, but we have the oxidation, we have 4 oxygen. That likely to be -2 oxidation number times 4. And if we solve for the sulfur here, we know that the sulfur, which is N, plus -2 times 4 must give you -2. So that's a quick calculation. We can get sulfur equals to +6. All right. And at the very end, you can always check, right? So +6 minus 8 gives +2, and we're happy. So that's just a sanity check. We do it every time, assigning the oxidation number. Okay. Now in the potassium paramate, we can have potassium, that's our alkali metal, so it's always going to be +1. Oxygen is -2 times 4. We don't know what manganese is, so I'm just going to put a N here. And everything adds up to be 0. So we have +1 plus N minus 8 equals to 0, and apparently N here equals to +7. You can write +7 here. Right. So this part may feel like a review for some of you who took AP chemistry, but knowing the oxidation number, this is important when we're talking in chemistry. Well, if sometimes we'll just say, hey, that has a +7 oxidation number, and you need to know what that means. It's, again, the oxidation number, they're just fictitious charges people use to assign to these atoms in the molecules. They're not real charges. It's very useful. All right. Before I move on to talk about ionic bonding, do you have any questions? Yes?
Is there still that trend where it's like +1 +2 +2 for like boron?
Right, so if you think about it, what these oxidation number means is in a hypothetical scenario, we're thinking about how that atom can reach a noble gas valency. Right, so if we have lithium, it's losing 1 electron, means it's +1. So for boron, that's losing 3 electrons, making it +3. But again, it depends on how it's binding to other atoms as well. Yes?
Would oxygen or chlorine be more electronegative?
They're Right, that's a very good question. So oxygen and chloride are actually very comparable with each other. So for this course, I'll always tell you which one of them is more electronegative, or I'll give you a number, right? So here's the electronegativity of, say, sulfur and phosphorus. Can you assign the oxidation number afterwards? All right, so that's for the oxidation number. Now we're moving on to talk about chemical bonds. So again, this is the classical picture of chemical bond. We're still treating electrons as pure particles. It's not technically speaking correct, but it's very useful and gives you some very good chemical insights. So when we're talking about ionic bonding, here is what is happening. You can imagine ionic bonding is a full electron is being transferred from neutral sodium to neutral chloride, so that both of these atoms have the noble gas electron configuration, right? So we're just using the sodium chloride as an example here. So in sodium, it has one electron in its s atomic orbital. You can imagine lose that entire electron transferred to the chloride. Normally, we observe ionic bonding when there are two atoms of very large difference in electron negativity. So again, electron negativity, remember that trend goes diagonally all the way towards fluoride. So the more electron negative it is, the more likely that is a ionic bond. So again, back to our example of the sodium chloride. Sodium is a very electron positive atom. So we're imagining sodium losing one electron. So that's the ionization energy, the first ionization energy, if you may. And for chloride to gain one electron, that's the effective electron affinity. So we can do a quick calculation here, and you can soon realize it's not as simple as just like the electron is being transferred. Here is the calculation for our classical ionic bonds. So remember, our first reaction is sodium losing one electron to form sodium plus electron minus, right? So we're thinking about that electron that's moved all the way like infinitely apart from the neutral sodium atom. Second reaction of interest is chloride gain an electron to form chloride minus. So if we write the overall reaction from 1 and 2, what we're getting, on the left-hand side, we have neutral sodium plus neutral chloride to form sodium plus and chloride minus. So this process, we're thinking about sodium plus and chloride minus are infinitely apart. They're not interacting with each other. And here are some numbers. The first ionization energy of sodium is measured to be 496 kilojoule per mole. All right, that's to move the electron infinitely away from a neutral sodium. Then the electron affinity of chloride means that the electron that for the chloride to gain an electron is negative 349 kilojoule per mole. And just as a quick reminder, the ionization energy is a positive number, so this is an endothermic process. Right, it requires energy to remove that electron from the neutral sodium. And then the electron affinity is a negative number, and it's ectothermic. It gains electron for the electron, it gains energy for the electron to be attracted to the chloride to form the anion. But if we do the calculation here, so this is a reaction of, this is the energy associated with the first reaction. This is the energy associated with the second reaction. What we're getting is when the two ions are infinitely apart, I annotated it with the potential infinity. It basically just represents the energy of the above equation. That equals to ionization energy of sodium plus the electron affinity of chloride. And these numbers are given on top. If we do that calculation, what we're having is the first ionization energy of sodium, that's 496 kilojoule per mole, minus electron affinity of chloride, that's 349 kilojoule per mole. We do that calculation, you get a positive number of 147 kilojoule per mole, which is endothermic. All right, so this is a little bit counterintuitive. It's the fact, even if sodium loses an electron to reach the noble gas configuration, chloride gains an electron to reach the noble gas configuration. When these two charged particles are infinitely apart, it still requires energy to form these two ions. So what makes an ionic bond? So now we came to the point of thinking about the chemical bond. Now the sodium plus and the chloride minus are approaching each other to make a chemical bond. And here, when the two ions of opposite charge, in this case, we have the sodium plus and chloride minus, when they're approaching each other, the ionic bond that's being formed, the ionic complex that's being formed, is stabilized by electrostatic force. Right, so it's electrostatic interaction or Coulomb's interaction that stabilizes your ionic bond, making your ionic complex stable. Or mathematically, the actual representation of the bond dissociation energy or the bonding energy of an ionic bond. This equals to V infinity. Remember, this is what we calculated. This is just ionization energy of sodium plus electron affinity of chloride, plus the electrostatic stabilization, Q1, Q2, 4 pi epsilon naught R. So this part is just our Coulomb's potential, or electrostatic stabilization. So in this equation, we have several terms. Here, R is our bond length or internuclear separation. 4 pi, that's constant. Epsilon naught, that's constant. And then Q1 is charge of sodium plus. Q2, that's charge of chloride minus. Again, this is just using sodium chloride as an example. If we're having, like, say, calcium oxide, then it's a different number for the Q1 and Q2. So this equation provides a good estimate for the bond dissociation energy for the ionic compound. So this is the bonding energy, right? So this is how much energy, how much stabilization energy we have in an ionic bond. But in chemistry, we measure it as bond dissociation energy, or BDE, or like E dissociation. So the bond dissociation energy equals the negative of the bonding energy. All right, so this BDE is defined by the amount of energy required to dissociate an ionic bond. So let's do an example question together. Here, let's just say, given the sodium chloride bond length, which is our R in that electrostatic interaction equation, equals to 2.39 Armstrong. The V infinity equals to 147 kJ per mole. You can easily imagine I replace that V infinity with ionization energy and electron affinity of the certain atoms. Can you calculate the bond dissociation energy of sodium chloride? So again, this is what we have before, right? We have VR equals to, well, let's just V infinity plus the electrostatic stabilization, Q1, Q2, 4 pi epsilon naught R. So note that this V infinity here has a unit of kilojoule per mole. So we're talking about that's the V infinity for 1 mole of sodium chloride. So here we need to add the Avogadro number, which is a constant here. All right, I'm not gonna do the plug-in numbers with you, but again, here are the things. what's the physical meaning of these terms. So this is talking about the bonding energy. Or how much total stabilization energy are there in the sodium chloride bond, in one mole of sodium chloride bond. V infinity, that's the energy required for this reaction. We have neutral sodium plus neutral chloride goes to sodium plus chloride minus. And these atoms, these cations and anions are infinitely apart. And then when the sodium plus and chloride minus meet each other, they have the electrostatic stabilization. All right, so that electrostatic stabilization or Coulomb's force just inherently are there when you're bringing two charged particles together. So Q1 and Q2 are the charges of my sodium plus and chloride minus. If it's not, that's a constant, and R is our bond length. And here, that's our Avogadro constant. And at the very end, the question reads, calculating the bond dissociation energy. So for this, we have the bond dissociation energy equals to negative of VR. Right, so you can plug in the numbers and check your answer with the annotated note later. All right. So if we did that calculation, one of the things that we typically get is ionic compounds are very stable. Ionic bonds are strong, and ionic crystals, they're very stable, chemically stable. So why is it? If we're just looking at one pair of the sodium chloride bond, that bond length is not exceedingly strong. However, in reality, our ionic compounds nearly always form ionic crystals. What we're having is every green dot here is a chloride minus, and every gray dot here is a sodium plus. So let me just circle one of the sodium plus that's in the middle, right? And every sodium plus is being surrounded by multiple chloride minus. So depending on how that crystal is packed, every charged particle in that crystal is being stabilized by multiple electrostatic stabilizations. So that explains why in the solid structure of these ionic compounds, they are very stable. They're stabilized by multiple electrostatic forces, and that's why ionic compounds tend to have very high boiling point and melting points. And before we move on, I want to quickly mention stoichiometry and nomenclature of ionic compounds. So when we're talking about stoichiometry, you can also do that calculation by balancing the charge. So far we're working on sodium chloride, right? So sodium has +1 oxidation number, chloride is -1, and that's happy. But say if we have calcium, and we know that calcium wants to lose 2 electrons to form calcium 2+. Again, using chloride, or as an example, I want to gain 1 electron to get chloride minus. And you want to balance the electrons here. So that's why on the bottom, for each calcium to form calcium 2+, you need 2 chloride. So the total equation is calcium plus 2 chloride goes to calcium 2+ plus 2 chloride minus. Okay. And at the very end, we have nomenclatures. Typically, in ionic compound, you just have element cations that's going to retain the name of parent elements. So if we have like sodium chloride, right? Sodium is just sodium. We're not changing the name of the sodium. But for the element anion, you can add the IDE at the end. So chlorine is a chlorine element, and then chloride, that's Cl minus. And again, like calcium bromide is bromine, that's the element. Bromide, that's Br minus. But all my exams are open book, so I'm not going to test you on nomenclature. You just need to know what people are talking about when they're saying like calcium bromide. You should know that equals to CaBr2. Right? Okay. Before we move on to talk about covalent bond, I have one more concept in the ironic region I want to introduce, which is dipole moment and ironic characters. We'll see dipole moment in covalent compound as well, but since ironic compound has larger dipole moment, this is a better way to introduce it here. So what is dipole moment? What we're saying about dipole moment is how polar a bond is, or how much charge separation it is. So before when we were talking about ironic compound, we're acting as it is 100% ironic. If it's 100% ironic, means the sodium is going to lose all its electron, and the chloride is going to gain that full electron. But in reality, the 100% ironic compound doesn't really exist. It's always going to be some percentage of the ironic character. So that percentage of ironic character is related to the dipole moment, right? So that depends on how much charge transfer is taking place in your ironic bonds or covalent bonds. So again, using the sodium chloride as an example, sodium is an electron positive atom. So we'll have a partial positive charge on sodium. And then chloride is the electron negative atom, so we'll have a partial negative charge here. So different from the oxidation number, these partial charges, we're thinking about it as actual charges. And then when we're drawing the arrow for the dipole moment, we always draw it from the positive end to the negative end. And to quantify the dipole moment, we have the equation here. So what are these terms? This mu, it is a vector because dipole moment has direction, right? We're always pointing from positive to negative. That's where that little arrow comes from. It is a vector with direction. And that's our dipole moment. On the right-hand side, we have two terms. One of them is the charge. So that's a partial charge. And then Q, that's the distance between these charged particles. Again, it has that little arrow on the top because it is a vector. It's pointing to from the electron positive atom to the electron negative atom. Dipole moments have a special unit we normally use that's called Debye, or abbreviated in D. So 1 D, 1 Debye equals to 3.336 times 10 to the negative 30 coulomb per meter. So coulomb and meter, these are our SI unit. They're too big to use to describe our microscopic chemical bonds. So that's why people introduced a new unit called Debye. And since we nearly always work with bond length in Armstrong, we can do that conversion here. So the dipole moment, when we were using it as chemists, we normally just plug in that R, which is our bond length here. And that's a constant, that's conversion constant. You don't have to worry about. And then at the end, we have our partial charge again. And then the ironic character of a chemical bond is defined by that partial charge times 100%. So lots of equations, but actually when we're using it, it's relatively straightforward. The concept of dipole moment is a pretty easy concept, if you may. So one of the applications you can imagine is, again, we're talking about sodium chloride. We're focusing on sodium chloride today. Imagine a bond length for sodium chloride that's 2.364 angstrom. And given the dipole moment is 9.001 Dubai, can you calculate the ionic character of sodium chloride bond? So the equation we're using, right, that's just this equation here. So what we're plugging in, this R equals to 2.365. On the bottom, that's a constant, and that's given the dipole moment is 9.001 Dubai. You can do the calculation and solve for the partial charge here. And the partial charge delta equals to 0.792. Or the ionic character of sodium chloride is 79.2%. All right, the larger ionic character means you have more like ionic type of properties, means your molecule will tend to have larger melting point, higher boiling point, and more like crystal-like characteristics. All right, so that's the end of the ionic bonding part. See if we have questions. Yes. Right, so the question is there a continuum between covalent and ionic bond? So the quick answer is yes, there doesn't exist any like pure covalent or pure ionic. It's always gonna, even if your covalent bond will always have some ionic character. And even like sodium chloride, we saw this pure ionic, it's still like not 100% ionic. It has some part of the electron that's being shared between the two atoms. I don't think I can finish, but I'll try to introduce you the idea of covalent bond, and next Monday we'll pick up where we left over. So now we're moving to covalent bonding. Covalent bonding, again, different from ionic bonding. What we're talking about is atoms are having similar electronegativity. So different from ionic bonding, where the atoms have very large electronegativity differences. Here we're talking about atoms with comparable electronegativity, or electrons are shared more evenly between atoms. So here's a quick classical interpretation of covalent bond and why a covalent bond is stabilizing. So imagine you have two nuclei with positive charges that are approaching each other. Because they are both positively charged here, the nuclei are expected to repel each other. So you have a force that's repelling between the two nuclei. And here the shared electrons between the nuclei are expected to act like glue to hold the atoms together. So if you imagine, in this case, the electron in the middle will have an attractive force between both nuclei. So that means electron between the two atoms is more or less acting as a glue to hold it together. Again, it's not technically speaking correct, but just one of the useful concepts of classical bonding theory. So the major difference between classical bonding theory we're talking about right now and the quantum bonding theory, which we'll be talking about next week, is in the classical bonding theory, we're still treating electrons as pure particles. But in quantum mechanics, the electrons is distributed all over the space. It's not just one single particle. But in this case, in the classical picture, we're treating electrons as just pure negatively charged particles. So this is a pure covalent bond. Imagine just H2+, where you only have one electron that's shared evenly between the two hydrogen nuclei. In reality, it is more often when we have a polar covalent bonds. Means we have two atoms. They have different electronegativity, but they're not ionic enough. So using HF as an example, here the fluoride is more electronegative. So the consequence of fluorine being more electron negative means it's going to attract the electron more strongly. So this electron locates closer to the fluorine comparing to hydrogen. Or the other way to put it is polar covalent bonds means electrons are being shared unevenly. All right, so this is related to the dipole moment concept we just introduced. When we have atoms with larger electronegativity differences, again, electronegativity, that trend goes diagonal from the bottom left all the way to fluorine on the top right. Larger electronegativity between the two bonded atoms will lead to more polar bonds. We can use the same equation to calculate our percentage ironic character. So remember our percentage ironic character, that's just the partial charge times 100%. And you can calculate the partial charge from the dipole moment of a chemical bond. So in this case, in HF case, you need to know how to draw that that dipole moment from the electron positive hydrogen to the electron negative fluorine. And we have the arrow pointing to that direction. All right. And let's again do another example together. I think I have enough time to finish this example. So the example reads, you have bond lengths of HCl and HF given to be 1.284 angstrom and 0.920 angstrom correspondingly. You can also get the dipole moment of HCl and HF from reading the table. Can you calculate the ironic character for HCl and HF and just tell us which one is more polar? Just intuitively, you would expect HF to be more polar because fluorine is more electron negative. But we can quantify it by calculating the ironic character percentage. So again, the equation we're using here is the dipole moment over atomic distance or bond length over the 0.2082, which is the constant, and gives you a partial charge. And this partial charge can then be used to calculate the ironic character. So these are the equations we're using. All right, and now we can just plug in the numbers here. So for HCl, we can read the HCl dipole moment is 1.19 divided. So 1.109 divided equals to bond length, which is 1.284 over 0.2082 and partial charge. You can solve for the partial charge of HCl to be 0.180, which translates to the ironic percentage of HCl. It's about 18.0%. Not a very ironic bond, if you may. Alternatively, we can do the same for HF. Right, we're using the same equation here, just plugging the different number. For HF, we have the dipole moment equals to 1.82 equals to the bond length, which is C, 0.920 angstrom, divided by that 0.2082, and then the partial charge. You can calculate the partial charge of HF. That gives you 0.419, or the ironic percentage of HF is 41.9. So comparing these two numbers, this one is considerably more ironic. All right, so intuitively, we know that the larger electron activity differences between the two atoms leads to more polar bonds. by doing the calculation, you can also quantify that difference by doing the percentage ionic character calculation. Okay, we have some left over, which are like descriptors of covalent bond. I have only 3 minutes. I don't want to rush it. So let's see if we have any questions before we move on. No? Okay, well, good luck. I'll see you next Monday. We'll catch up here and we'll talk about Lewis dot diagram and VSEPR.